Okay, I'm going to start with a little demo. Let me first play these files. I hope that these sounds come through in the video recording. Let me just check. So here's the OGG versions are basically for processing. So I hope you can hear. I have two different whistles that I've recorded. Let me play this. Okay, that was one whistle done a couple of days back. This is a whistle done today. I'm not a very good you can see that I'm not great at whistling. Some of you may be very good at that, but here's my clapping. That is noise. You see, the whistle was more pleasant. This is really irritating, isn't it? So this is noise, and that was okay. So let's do some. What I'm going to do is some processing, and I'm going to use Octave to do this. There's something called an audio read, which simply reads this file and then reads off the signal. So let's go to Octave. This is my Octave page. Anyway, for those this is very similar. In fact, this is the precursor of MATLAB. So a lot of things you can see that I'm already in the directory where I can upload these things. So there's a command called audio read. You can do something more than so I'll call it Y1 and FS1. So this Y1 is basically the signal. FS1 is the sampling frequency. For those who are familiar with audio, digital audio, the sampling frequency is dictates how many the every delta t that I am capturing is dictated by this sampling frequency. So we use this audio read. Let me see, audio read. Let's try to read. It can read only OGG files. So let's select let's say my whistle 2, right? Or maybe my whistle, okay, 2. I hope it reads. So it's read all these. So these things that are, I should have ideally put a semicolon at the end of it. There's a lot of data that it is reading. These are just numbers which kind of dictate the amplitude, which is possibly voltage coming through your microphone, which I had used for recording, standard computer microphone that I've used for recording. So there are, you see that the sampling frequency is 44,100, which is typical of audio recordings, 44 kilohertz. So what it means, the reason 44 kilohertz is chosen is that, remember we said human hearing can go up to 20 kilohertz. So the usual thumb rule is to use typically something with the Nyquist sampling theorem. Shannon-Nyquist sampling theorem says that you should sample it at least at twice that frequency, so which is 40 kilohertz. But we allow a leeway, and then for the windowing function basically. So typical sampling is around 44,100. So let me plot this to get you a visual feel of how this would look like if I record this from the microphone, the waveform, the signal, how does it look like. So let's look at plot Y1. So you can see this is my whistle which has been plotted. You can, of course, this is only the number of points. I can turn that into time by using that sampling, right? So you see, it's fairly impulsive. Whenever I whistle, it looks like I whistle. Of course, there's a gap, and then I again whistle, so on and so forth. So so you can see at some points of time I have been able to raise my whistling amplitude. At some other bands have not been so good at the whistling part of it. It's okay. So what we are going to do is to try to process this signal. So one thing is that you can see that the amplitude of course varies, but what is the frequency content in this? So that's something. So I told you in sound there are two things that are important. One is amplitude. Obviously you can see that the sound amplitude is lower here, somewhat higher here, and then again it goes down, and towards the end I was able to sustain this amplitude for a while. But what are the frequencies associated with that? So let's there's a command simply we will say y1f, which is FFT is a simple command which does the fast Fourier transform of this. So we plot that, and then we say, okay, look, I want to plot the magnitude of y1s, because when we do an FFT, we will get both the real and imaginary parts. So I want to do this because this is the entire spectrum, which of course is not valuable. But you can see somewhere here, maybe you don't see much happening after about 50,000 points. Now, what do these frequencies correspond to? That has to come from the sampling frequency, or delta f, and the overall time length for which I recorded. All these will have to be put in to calculate the exact frequency. But you can see that so usually when you do an FFT, there is a mirror image, so we don't need the data that is on this side of it. So typically we draw a line at the middle of this, and we only look at that. So let me replot this with say only about 30,000 or 40,000 points. So let's look at that. Okay, oops, what happened there? Yeah, I forgot another bracket there. So anyway, I know, so somewhere around these frequencies, you can see my whistle has a lot of content around this, and there's not much beyond that. So whistle typically will have very focused energy range, frequency content, which is typically in this range. It just turns out, of course, this is, I can tell you before we process this is about in my view, this will be about, if I'm not mistaken, this should be about 2 kilohertz. Okay, I will post this. Of course, what I will do is I will process it properly with the octave commands and so on and so forth. So just to get you a feel, so you can see whistle is basically very focused, sharp energy around this, and then there's something around here, which is around here, but most of the energy is concentrated here, which is about 2 kilohertz. That comes from the whistling. So my throat is tuned to 2 kilohertz. Of course, this will vary from person to person, but interestingly, even the same person, depending on how we whistle, can change this frequency. So we will not get into that, but just to get you an idea. So you can see this is the characteristic of the sound that has been captured, which is a dominant energy is around 2 kilohertz. Amplitudes, of course, you saw was varying here and there. Okay, let's make one more attempt at we will now go back and load, instead of my whistle, we will load, let's say, my clapping. My clapping, January 30th, 21. Oh, oops, I should have again put a semicolon at the end of this. It's now reading the data that is sitting there in the clapping. We'll follow the same process. I will plot first the time history data, how the clapping looks like. So typical response, and it is periodic. Of course, I kept clapping at regular intervals, so we will see that also. Let's look at that, shall we? This has a lot more data points than the other one, I suppose. Most of these will be sampled at 44.1 kilohertz, which is typical. That's kind of typical, and I'm just waiting. I should have probably put a semicolon and saved ourselves some time. But it's okay, as this is scrolling, I can keep talking about other things. So clapping is also, so again you see 44,100 is the so let's first plot this. Okay, again the time the time data, so 44,100, and let's look at the size of this recording that I have, size of y1. So you can see there are 347,904 points. Now remember that the sampling frequency is dictates delta t. So delta t will be 1 by fs1. Okay, so so it starts from 0. So if you look at from a time history standpoint, so I will call it t1 will be delta t times 0 to this number, which is 347903, because the first one is supposed to be 0, right? So if I do this, so this is my t. So let's say max of t1, which will tell me the time window. So I have recorded for about 7.9 seconds. So that is the length of the recording that I have done. Alright. Now delta f is actually dictated by 1 over t1, max of t1. So anyway, these are signal processing things. I am not getting into this. The reason is because I now have a delta f. I can now tell you what the frequencies are. Okay. Alright, so let's do the same thing as we do before. y1f is FFT of y1. Okay. Now, so first of course let's plot t1 comma y1. That will give you an idea of, so we have plotted that. Let me go see figure 1. So you can see I have been quite consistent. I have been clapping fairly regular intervals. I have been very good at maintaining a periodicity. And you see the interesting feature of this clap. I do this and then it decays, and then after it has decayed, I will come. But if you do this, then before the full decay happens, the other energy starts to spike. But I waited for this to kind of die down. So you can see the sound that I created by clapping is an impulsive sound, and then it decays. So now we are interested in seeing what is the frequency content associated with this. So let's look at, go back to the Octave screen. So let's say that now let's look at, so since we have a large number of points when I do an FFT, so size of y1f will also be very large, the same size 34794. So usually we partition this into half. So we'll say ff1 will be delta f 1 delta, did I call it delta f, or yeah, delta f star. We go from 0 to we'll go to 347904 by 2, so 0.5 times 347. Okay, max of ff1. So because I have taken this window, you see we are going up to 22 kilohertz, which of course has no meaning. You won't be able to hear at that kind of a range. So let's now plot, we will do a plot ff1 comma absolute of y1f of 1 colon 0.5 times we'll have 347904 by 2, right? So we'll do 1 colon 1 plus 0.5 star 347904. That closes that, and this closes this. So you can see, I'll move myself out here. You can see that this has a lot more energy content and it is at the lower frequency. I told you my whistling. So you can see by clapping we create a very broadband sound. So that broadband means a lot of frequencies that are there. Maybe we will reduce this even further. Let's say we plot only up to 5 kilohertz so that you get a better feel of the energy content that is there. So let's say that I do ff1 of say 1 2 about 170,000. So let's say plot 80,000. Good. Now you can see that it's a little more So you can see I have my whistle, you could see was very focused around, you have to believe me that it is around 2K. So here, but you can see the clapping produces sound which is basically very broadband. So this is one of the things that makes these type of sounds more irritable. So that was like almost like a, the whistle is like a tone. Not quite, because there are some energy around that frequency also, but it is more or less close to a tone, whereas this is more broadband. Clapping is basically more broadband. Alright, I hope that now you have got a good feel of this. So let's let me leave myself there. Let me go and pull out, now let us open my presentation. Let's go back and look at where we were. So let me move myself down back here. So we said the levels and amplitudes, we have looked at these things. So we measured sound pressure. Of course, the pickup is basically a microphone, but remember that in real acoustics we use better high quality microphones. I just wanted to use the standard microphone that is available in a laptop. The basic idea is the same, but the fidelity is not as good as what we use in the lab. So you could see, of course, amplitude, of course these are things that are features that you will observe, because if I clap here and you are very near me, you will hear it to be very loud, but as you walk away, the sound that you sense, the amplitude that you sense, the frequencies don't change, but the amplitude that you sense comes down. So this is a characteristic of sound waves. So this in typical thing, sound pressure is usually, let me close this here. Sound pressure is usually measured by microphones, just like what we have measured here. And in water, this microphone is called a hydrophone because it is in water. Now, earlier I had mentioned that the amplitudes can span from 20 micropascal, this pressure fluctuation that you sense as sound. 20 micropascals is the lower limit of what you can sense for a normal human being. And upper limit is 10 pascals. Of course, there are very, very special cases where it can exceed 10 pascals, but we will not worry about it. Typically, the range is 20 micropascals to 10 pascals. So you can see that the order of the sound pressure amplitudes is from 10 power minus 5. 20 micropascals is 2 into 10 power minus 5. 10 power minus 5 pascals to 10 pascals. So that means I am spanning 6 orders. So this is difficult to do on a linear scale. So therefore, we go to a log scale. So you will see that the sound acoustics community always uses a log scale to express the sound pressure amplitudes. And it is called as one of the fundamental things that is measured is called sound pressure level, which is expressed in dB. So the sound pressure level is 20 log based on PRMS by P reference. How do I get this PRMS? You saw the signals that I have stored. I can get the mean square value of the signal and then take the root mean square, root of that mean square value. Then I will get the PRMS. So from the recordings I can generate that PRMS. The reference is of course taken to be 20 micropascals because that is the threshold of human hearing. So if I had a PRMS of 2 pascals, then my LP, which is the sound pressure level, is 100 dB. So you can see the formula 20 log based on PRMS by P reference. So if I had PRMS equal to P reference, I will get an LP of 0. So 0 dB corresponds to threshold of human hearing. Now this PRMS of 2 pascals, by the way, is considered very loud. So just to give you a thing before we sign off with this lecture, let me go and show you a picture of the range of sound levels that we normally have. Because 0 is the threshold of human hearing. A very silent study room is around 20. Typical classroom chatter, it says, is 70. Unfortunately, the classroom chatter for a year due to the pandemic has been away. If you go to a construction site, so this is 100 dB is like being in a construction site. I'm sure some of you would have, with IITM having a lot of construction happening, you would have heard the construction sounds. So it's quite loud. 100. So you see the color is an indication of the severity. So you don't want to be exposed to this construction site sounds 8 hours a day. You will go deaf. So you can see a jet taking off and you're 200 feet away, that's about 130. That's very loud, and threshold of pain is 140. So which is why I pegged something, my 10 pascals is below the threshold of pain. So you can see various activities will fill into this. In the typical conversation, you and I sitting and talking is only about 60 dB, assuming that the ambient is if you are sitting in IIT, it will be probably 60 dB. But if you are sitting where I am outside campus, it may not be 60 dB, because the background, there are a lot of cars, motorcycles and others running around. Okay, I think we will stop here and then move forward. I hope you have been able to get a feel of this that sound classification, two qualities that or two characteristics that we look for: amplitude, which I have done through a clapping and a whistle, and the frequencies associated with that. So these two are important characteristics that dictate when we study noise control, and then we target, okay, if I want to reduce these frequencies, what should I do, and so on and so forth, comes from as a control aspect of it. Okay, we will stop here.